Don't you love it when you're learning about something and things just click? Like a light switch. Clicky switches they're pretty fun. But why do switches make noise? What's the point of all that clacking? Well, it has to do with the fact that you've been lied to. But let's not get too conspiratorial just yet. First, let's look at some of the switches that don't click, because there are some. This electronically controlled dimming module turns the lights on completely silently. No clicking there. Then again, this other one that's not a dimmer makes a pronounced clicking sound. And I didn't even touch it. What gives? Well, the dimming module is using a solid-state device known as a triac to actually turn the lights on and off, so it's not quite what I mean by a switch. This standard thing goes on or off module does in fact use a type of real switch to do its work, so you hear a click. Same with this toggle light switch, this rocker switch, this rotary switch, this lamp cord switch, this power button, the rocker switches on this studio light, oh, and the big one too, this toaster, the mode selector on this space heater. Even its thermostat makes a distinct click. But why? Why be so clicky-clacky all the time? To start to answer this question, we first need to answer a simpler question. What is a switch? Well, a switch is a handheld game... No. A switch is a mechanism used to divert rail cars from... No. A switch is the simplest mechanism that can control the flow of electricity. Say you have a simple table lamp and want to connect it up with the power grid. Well, we simply take its bare wires and carefully touch them to these live wires and voila! Let there be light! Now to turn the light off, all we need to do is carefully pull those wires apart and hope the live ones don't touch. But this is pretty dangerous. Even Edison knew that. So we designed electrical sockets which contained live wires behind an insulating barrier. And we designed plugs that would, depending on your country, somewhere between somewhat safely and completely safely, allow you to make and break electrical connections. But this isn't the most convenient way to turn something on or off, and most importantly, using them that way isn't good for your plug or your receptacle. See, if I take this lamp and plug it into this outlet, it lights up, no problem. And if I simply unplug it, it goes out, also without a problem. But watch what happens if I take this space heater and unplug it while it's running. Ooh, that was quite a spark. Let's do it again. Ooh, let's do it again. Ooh, big one. Let's do that again. Let's do that again. While this specimen continues to be amused by the sparks, we'll move on to the next jump cut. Ooh. When the heater is running, a lot of electricity is flowing into it through this cord. 1500 watts, in fact. To stop that flow of current, all we need to do is put an insulator between the contacts of the receptacle and the pins of the plug, which of course we can do simply by unplugging it. But when we unplug it, it doesn't just stop the current flow right away. There's a brief moment where that current manages to jump out from the outlet and the result is a spark. The same thing happens if you plug in the heater with it turned on right before the pins of the plug and receptacle first make contact, but the spark usually isn't as large as when an active connection is broken. And this is where you've been lied to. See, when you were little, you were probably taught about electrical conductors, like the wires in this cord, and electrical insulators, like the plastic insulation surrounding that wire. If you had a really nerdy teacher, you might have learned about semiconductors, but lots of us were sorting things into the two categories of insulators and conductors. The lie is that, just like most things in the real world, the electrical conductivity of any given substance exists on a spectrum. Everything conducts electricity when you try hard enough, even air. Now we rely on the resistance of air all the time. Electrical transmission lines are typically bare aluminum and are held up in the air by stacks of insulating discs. The higher the voltage of the line, the more of these discs you need, because even they aren't perfect insulators. Nothing's a perfect insulator. And that's the problem. Air's pretty good, and when you unplug something from an electrical outlet, you do disconnect it from the power grid and stop the flow of electricity to it, precisely because there's air now between the pins of the plug and the conductors in the receptacle. But when you pull that plug out of the wall, there will be a brief moment when there's only a tiny bit of air between the plug and the socket. And this is not good. When those contacts are close but not quite touching, the air gap is so small that the breakdown voltage, that's the voltage at which an insulator fails to stay an insulator, is lower than the voltage of the electrical supply. This means that the current will actually jump the gap, and this creates an arc discharge. That's the spark you see here. Now on its own, this isn't particularly bad. Thanks to the fact that we use AC power, the voltage crosses the 0 point 100 or 120 times per second, so that arc will usually go out nearly immediately, though it should be noted that arcs can be sustained on AC power. More importantly, the breakdown voltage of any insulator, including air, is a function of how thick it is, so once the contacts are just a millimeter apart, that arc will generally be unsustainable. But here's the problem. That arc is hot. Very, very hot. So hot, in fact, that it can burn the ends of the plug in the socket. So we don't want to rely on pulling the plug out of the socket to stop current flow. What do we do instead? We use a switch. All the switch does is create a break in a circuit. There are many different types of switches, but they all do fundamentally the same thing. There are two electrical contacts, and they're either touching or they're not. If they touch, current can flow, and if they don't touch, current can't. But then switches do the same thing as unplugging it. Don't they have to worry about arcing? Yes, in fact, even more so. Electrical arcs damage electrical contacts in various ways, but among the most significant ones is that the contacts eventually melt away. See, each time there's an arc, that plasma is so hot that the surface of the contact briefly melts, and that material can sputter off of it. Additionally, the high temperature can cause corrosion of the contacts, and you get lovely issues like carbon buildup, which increases the electrical resistance of the contacts, and that's not good. Even better, if the arcing is bad enough and the surface of the contacts get hot enough, they can weld together and get stuck closed. I guess that light's on forever now. Since the contacts in a switch are generally pretty small, we want to minimize the arcing that can happen because, well, an arc will warm them up quickly and cause all those problems I was just going on about. And how do we do that? Why, with speed. Remember that household voltages are low enough that an arc generally can't be sustained once the contacts are just a millimeter apart. So if you get them apart quite quickly, any arc formation that does occur will be very brief and unlikely to cause significant damage. And that is why switches click. Switches are designed with mechanisms to ensure the contacts open and close very quickly enough to prevent an arc from lasting more than maybe a millisecond or so. Effectively, the contacts are meant to slam together and then get yanked apart, and that makes an audible click. The mechanisms that accomplish this are often ingeniously simple. Many times it's just a spring cleverly integrated into a pivot. Let's take a look at a simple household rocker switch. This switch is nice and clicky. Who needs a fidget clicker when you can just run to the hardware store and get one of these? This design is almost devilishly simple. Below the faceplate are 3 pieces of brass, 2 of which are the same ones you attach wires to on the outside. The smaller one holds an electrical contact, and the larger one serves as a pivot point for a small swinging piece that holds the other contact. If there's a torque applied to the swinging piece in this direction, the contact does not touch the other one, and no current can flow through the switch. But apply a torque in the other direction, and now the contacts touch. Current flows into the switch through this terminal, through the basket thing, into the swinging thing, through the 2 contacts, and out the other terminal. All it takes to ensure the swinging contact moves quickly is a spring. See, the rocker paddle that you touch is in fact the same thing moving the contact. These grooves hold on to the edge with a little play, and when the rocker rocks back and forth, so does the contact below. But thanks to the spring, the rocker, and more importantly the contact, wants to stay in either position. The spring gets increasingly compressed as the rocker meets the apex, and once it passes it, bam, the spring expands and pushes the contact in the other direction. The result is a swift action in both directions, minimizing arcing. Pretty clever. Unfortunately though, this switch design isn't perfect. In fact, many, if not most, switches on sale today aren't. See, you can actually move the contact a bit before the spring takes over. If you carefully apply pressure on the switch, you'll see that the light goes out before it clicks into the off position. Listen carefully and you can actually hear arcing going on inside the switch. This isn't really great, especially if you have a lot of lights on the circuit you're controlling. In fact, you can see on these contacts that they have been slightly damaged, and this isn't a very old switch. I know because I installed it myself. Granted, most people don't turn the lights on and off like this. If you do it like a normal person, then the contacts are swiftly moved and arcing is minimal. Still, it annoys me that it's even possible to damage the switch at all. Many switch designs, like these lamp cord switches, are simply impossible to hold in a half-on, half-off state. Sure, they're not designed to carry the current of a normal light switch, but I bet these guys rarely ever fail from bad contacts. And normal switches can be made impossible to abuse. The house I grew up in was quite old, and a few rooms had toggle light switches that you could actually move nearly completely into the opposite position before the internal mechanism opened or closed the contacts, with a very loud clack. Those switches were in service for 50 or 60 years, and likely still are. Granted, they were only controlling a single light in all but one case, if memory serves, so they weren't ever under much electrical stress, and they required much more force to use than modern switches, which is probably why that style went out of favor. But this paddle-style dimmer switch has a mechanism that prevents partial making and breaking of the contacts without requiring significant force. You can see that even if I use my two thumbs on both sides of the switch and very, very slowly move the paddle, the lights only go on and off with the click of the internal mechanism. This design here is what I'd call ideal, and it proves that easy-to-use switches can still be made with a fast, clicky, abuse-proof mechanism. So if you're shopping for a light switch at a hardware store, tactile feel of the switch does actually matter when it comes to switch longevity. A nice, solid snap makes me more confident than a smooth, quiet movement. This cheap toggle switch is what I'd consider awful. The toggle moves smoothly without much resistance at all, and the contact is actually broken when the switch has barely moved out of its resting position. It actually requires conscious effort to ensure the contacts are quickly moved apart, and I doubt this switch would last more than a decade on a circuit with more than a few lights. In fact, it's not even fair to say that this switch actually clicks. It more or less thuds. Any switch that's designed to interrupt even a modest current flow should, in my opinion, have a nice audible click. That plug-in thing goes on module? It's got a relay in it. Relays are electromechanical devices that control large currents with small currents. Essentially, they're a switch with some sort of external control. In this case, the small computer inside here will turn on the relay when it's been asked to, and click, the light goes on. The contacts in a relay are closed via an electromagnet and are held open with a spring. And as luck would have it, this simple arrangement means the switch opens and closes quickly, and so it clicks. Fun fact, when we need to automatically control very high current loads, we use what are essentially large relays, but we call them contactors. Contactors often just use air to break the circuit like any other switch, but when we get into high voltage applications, the contactor might be contained in a vacuum. And in really high voltage applications, like in power grid substations, you might find switches and circuit breakers inside a volume of sulfur hexafluoride, which is an incredibly good insulator, and this is in fact the primary commercial use of SF6. Now, not all switches need to click. Switches that don't carry a lot of current, like the clicky buttons on your mouse, don't need to click at all because there's not going to be any arcing going on in there. They click mainly because that style of switch is designed to provide a lot of tactile feedback. And actually, a very clicky switch can be a disadvantage in digital devices because now you might need to implement some sort of debouncing, but that's beyond the scope of this video. So, now you know why switches click. They're really just prolonging their life. And if you want to prolong the life of the switches in your life even more, be sure you always give them a good flick, or poke. Since many modern designs kinda make you a part of the contact closing and opening action, you can and should click to your heart's content. Thanks for watching, and thank you to the fine folks supporting the channel through Patreon. I really do appreciate your support. If you're interested in joining these people and supporting the channel, you can check out the link at the end screen or in the description. Thanks for your consideration, and I'll see you next time. Nope. I messed up. I thought this would go quickly. It's not going quickly. So if you get them apart quickly... That was going well, but then it wasn't. Wrong pronunciation. No, that's the wrong way. Now, no, I don't like how I did that either. Well, that might have been... never mind.